Um, I I uploaded a little like attempt at explaining how to install uh, uh, how to install the Scatman thing yesterday on the Google Drive. But I didn't send around an email. I probably should have done that also. I just wanted to hear, has anybody tried that? Could you get it to work? Or I think there's some errors in it because I tried helping somebody else set it up and it didn't work. So yeah, okay. No, I'm assuming this means that it worked flawlessly for everybody, and we're all just waiting to get on with the program. Um, yeah, I mean, let me just make sure. Just share my screen then. Can I do this? Okay. This is the wrong Jupyter. So the way I have it set up right now is there's this, there's this, there's some things you can do with if you build Scatman directly from source, which you cannot do otherwise. Um, so I have it set up in a little Docker container where I just installed all the prerequisites and um, yeah, made a VAENV, a virtual environment and stuff like this. This is very similar to what you would end up with if you did uh, there's some instruction for how to set up Windows subsystem for Linux and how to, yeah, I only tested compiling it under Windows subsystem for Linux, but um, all the other things should also work. Let's see, code, EBI detective. So what I put together, which you can also find on the Google Drive, is it's just this little folder. And yeah, there's some instructions, which again, I realize I should, uh, these don't really work that well because UV requires a file called pipe. Anyways, this is all not relevant. But there's like a folder full of patterns and a folder full of plots, and I thought it would be a fun semi-activity to you could try to if you want to try it, if you want to have an excuse to play around with this Scatman, you can try to replicate these. But it should work to just like you navigate to the folder and then you run Jupyter. Ah, sorry, I need to activate the environment first. So here it is. Let me just make it a bit bigger. Okay, can everybody see this? Is it super super? Yeah. So yeah. I mean, anyways, let me just start out by talking a little bit about Scatman, and then we can talk about if yeah, if how much more time we should spend. But the Scatman generally works through this multi-slice Fourier transform technique, which is basically you step through whatever target you have in slices, and then you can get contribution of each slice to the final diffraction image by doing a Fourier transform through the slice. Um, and that means generally the way it works is you import it. This is just a Python package. Um, And if you guys have any questions on the way, please just interrupt. Um, then you have to set some parameters. So this is the resolution of your detector. Right at the end, we want to have these nice uh, these are the kind of diffraction images that we are trying to get to somehow. So you set a resolution, you set a angle, um, and then you set a wavelength. And this wavelength, this is technically a unitless parameter because or not, it's not unitless, but you just set it to whatever unit that you're using to set your shapes, which we will come to in a little bit. So I'm just doing nanometers. Yeah, then you set your experiment, and then you need, of course, uh, how the optical parameters of your target. So these are the delta and beta parameters. And then you create a detector. This detector is the MSFT. This is just directly the output of your. Um, actually, let me go to this folder instead. Yeah, MSFT is directly the output of this MSFT algorithm. There are some other detectors. In general, the online manual is quite reasonably well put together, I would say. But there's some other detectors, and the things the other detectors do is that you add then shot noise, not shot noise, but like yeah. So there's an ideal detector. Actually, let me just show you. This is the MSFT output basically, and let's swap the detector. Hmm, strange. This doesn't look like it should be. Ah, okay. Narrow here. Just remove this. Again, it's a bit messy, this code. I'm very sorry. I made this late last night because time management is apparently hmm, okay. This is didactically a little bit bad because I was hoping there would be a bigger difference between the two detectors. Let me increase the angle. So let's go out to 5. Then yeah, this is how the output from this MSFT detector looks like. And we swap it to ideal. Okay. Yes. If we swap to ideal, then it changes from being uh, in units of yeah. Anyways, MSFT is like just whatever the output is, but this ideal you then add okay, each pixel has a Poissonian chance of getting a photon, and that means there's gonna be some noise out at the edges. Somehow it's not present here, which I don't understand why not. Try to see this. Hmm. Okay. Of course, when you have to translate it from this MSFT thing to like a what would it look like on a detector? Um, then you also need to add a um, you need to set the intensity, and the intensity is set automatically by but you can also set it. I think it's in here. There should be an intensity slider. No. And this is one of the few things that's like, um, otherwise, wavelength and shape are the only thing you need to worry about, but intensity is also has distance units, right? So if you're changing, anyways, yeah, this is. But the general way it works is you generate a shape, and then you pass your shape to the detector. So detector dot acquire shape, and then out comes your diffraction image. And this is sort of the, yeah, this is the quick and dirty of this program. There's a lot of different shapes. So I have a link here to the shapes part of the manual. What you will notice if you look through these is they are, yeah, they're all very droplet oriented. They make wibbly wobbly shapes, and there's no simple way to make, if you have let's go back to this. I think we might have seen these images, hopefully, at some point during Marcel's lectures. If you have like nanoparticles, which are crystals, obviously these have some sort of crystalline structure. And this you can do, but it's a bit more complicated because this program is made for yeah, wibbly wobbly shapes. So yeah. Are there any questions? Okay. Um, yeah, we can. Yeah, I can show you this detective framework I made. This is if you want to have an excuse to play around with it. As I noted, I made these test images. You can try to grab some shapes and see if you can um, find the thing that makes these shapes. These ones are quite fun. You might recognize them from um, yeah, some images we have looked at earlier. But yeah, maybe we should. I guess I can either talk a little bit about how you would work with this in like a more uh, direct sense, or we can try to work through these plots. Are there any thoughts on either or from you guys?
Yes, we can do
Uh, yeah, but are you, would you be more interested in like I could talk a little bit about how like when the thing you actually use this for is obviously you're doing somehow you wanna fit a shape to I don't know how much I actually have to say about this, but yeah. Let's just look at this guy then. So this is any guesses for a shape? We're starting off on an easy one.
a split.
Sorry, a slit or what did you say, Alap?
Yeah, that's what I told you.
Circular hole.
Yeah, it's a good guess, but of course these things we are imaging are small particles, right? So you're on the right track. shape-wise, but it's not a hole. It's the opposite thing.
Okay.
So yeah, this is a um, I I think I did this thing trying to render the shapes. Uh, okay, spoiler alert, but it's a ball of
Yeah.
uh, of hard-edged. This next one is probably only interesting if you're really trying to fit to it. So yeah, you might notice there's let me put this down here. Okay, obviously these have different. I don't think they had this one. Okay. So there's different frequencies.
Yes.
What is this? What does this tell us?
Second
Guessing.
one size is larger as compared to first one, but it will also is spread.
So it's larger and also what?
Spherical in shape, spheroid, nanoparticle.
Yeah, they are both spherical. I think the difference should be that this. What did you say it was? Sorry, it's a little bit hard to hear you. No, something with hard or.
It will be hard.
Mhm. Yeah, this one is hard and obviously bigger. That's a very good, very well recognized. This one is softer also outside of being, but this is not as easy to see on this diffraction pattern. But I think mathematically, if you soften it, because this can be seen as you are Fourier transforming, right? If you soften it, you can think of that as convolving the sphere with a Gaussian. And if you do this, then your Fourier transform is also multiplied, right? This convolution theorem for Fourier transforms by this Gaussian. So what should happen is the should broaden out a little bit, but it also looks like there's some beating happening. This yeah. Actually, let me quickly double check my note. My yeah. The other thing is there's a generate test case. So if you want to cheat, you can also just look in this. This is the program I use to generate all these with. But let's let me open it on a second screen where you guys can see it. Double check that I'm looking at the right shape for the right thing. I don't know why it refused to be moved. Okay, so okay, yes, yeah. The number one here is this is a soft shell, so it should look. We go back here to shape renderer. This you cannot see, but this is one of the things you can get. You get if you compile it from scratch. For each shape, there's a get function, which will just give you like the um, it'll give you the density, so to speak, of the. But you won't see what is soft here is that there's a transition from the helium delta and beta parameters which I've just used for everything, into zero. So you don't see this here. Uh, Here's another one, and I think this is another. Yeah, these are all using this shell sphere shape. So we've had soft, we've had hard. What other variation can you think of? If it looks like this, uh, then the hard sphere is just you set right the sphere radius to something, and then you set the thickness of the shell to 0, and you set this transition width also to 0. This is thus determining how smoothly these two things transition from one another. And then you set the delta and beta to something, and you don't care about the delta shell and the beta shell because nothing is delta shell and beta shell. For the smooth one, you can do it very similar. You set the sphere radius to something, you set the thickness to something, and then you set a width. So it goes from inside the shell to outside the shell, and then you just set the outside shell parameters to 0, and then you get this smooth transition. So, yeah. See, just grab grab image 2, load it in, and see if we can have a look at it. Compare it to this other thing. So image 1 is the loaded shape, I think, the loaded diffraction image. And yeah, okay, this is obviously too big. Try to set the shape a bit smaller. This is now too small. Mm. So somehow it works for the first beat, but then it gets off on the second beat. So probably right now, you can see this shape I'm trying to compare it to is just a shell sphere with a hard edge, right? And there's a radius, and then there's no, yeah, no transition. There's no shell outside, rather. Are there any guesses for what we could try to compare it to otherwise? I can tell you it involves doing this. It's a bit of a spoiler, I guess, but So what are we doing now? We are setting the inner part of the shape to 0 and 0, and then we are setting the outer parts to. So this is like this would be equivalent to vacuum, right? And then the outer parts have helium. Uh, is that a? What, oh, sorry, were you saying something, Umesh? Or
No.
okay, good. Yeah, but anyways, let's see how. Actually, let me quickly do no. But so if we set a bit of an outer shell, then what we're looking at is yeah, it's a hollow ball basically. And then this is probably a bit big. Hurrah! There we have it. Isn't that nice? Yeah. So, um, I don't know how much didactically there's in going through all of these images, but I can talk a little bit about and give you some hints for the general ones if you want to play around with it. Or yeah, does anybody want to try does anybody want to try getting this Scatman around on their PC? Or we can also try. I have tested it now on Windows, but the instructions I left were a bit poor because I did this all a little late. But if you are gonna try it running it on Windows, you need to do this installing WSL, and then the simplest thing would be to do like native Python or Conda or yeah, one of the. But actually, compiling Scatman is not that complicated. If you have like a clean install, then uh, you should be able to run almost this. Let me just add a little bit more, which I found out you also need. So um, basically, you install Python, you install I think these are development headers for Python probably, so you can compile stuff against your Python installation. And then you need a compiler for the Scatman instructions say GCC, but I've had trouble without this G++ also. And then you need this libFFT3. This is the thing that makes the whole thing work. It's a fast for it's a fast Fourier transform library. So what we're doing, of course, is we're stepping through our shape and Fourier transforming every layer. So you need something that does Fourier transforms very quickly. Yeah, but then like you can run these things, and also it's a good idea to have Ski installed. And then this should work. If you're on WSL, when you run this Jupyter it will not automatically open a window. So you need to go to, right, here's the kind of console output you get when you run Jupyter. Just need to go grab one of these links and paste it into your web browser. But yeah, this was another thing. That is there anything else to note? I don't know. I made a little because as you can probably guess from these later plots, these are not round things anymore. So I made a little helper library called shape functions to just generate differently shaped regular polyhedra. So one of these shapes that Scatman has, if you are out on this, you really want to do something strange, there's these 3D volume shapes. So this volume map works by just giving it you give it an array of zeros and ones, and every place there's a one, there's a bit of your shape in it. So here you can even do like, I don't know, duck shapes or whatever if you want to simulate that. I don't have a good duck model, sadly, too. But yeah, anyways, so these ones are just made to plug into this volume map, and yeah, it works more or less. Volume distribution is you can get even crazier here. You directly have every entry has just its complex refractive index. This can be really nice if you're doing something strange, like for example, if you'll permit me to share a bit of the stuff I used it for. This is not but so there's this concept of, oh, sorry, right, nano. Um, these helium nanodroplets or nano targets in general, you can make explode into plasmas, and there's been some people that have identified. That's not the one I wanted. But basically, these plasmas you can see on. Rather, no, sorry. If you make these plasmas under the right circumstances, you can get shock waves in them, and this you can see in on BMI images. So one thing I have used, this is a proposal we sent off to XFEL. We wanted to do the same thing, but instead of doing it on BMI, we wanted to do it on using coherent diffraction imaging. So yeah, this is, where did I put this? I think it's in here and then here. So what you can do with these, like, it's not the file I wanted. You can make a model for your nanoplasma explosion, right? And then you can evolve this model, and then you can transform this model of your nanoplasma explosion into a volume for doing this, and then you can sort of try to track. This is the radial distribution of the simulated image in time. And so this is one thing you can do with these like very flexible shapes. There's also like these cube maps and spherical harmonics. So if you have something, one example could be you have some shape that is in the process of becoming a nanoplasma. I believe the common image here for helium nanodroplets are usually right spherical, but once you start igniting them, they start wobbling, and this is something you could model with these this cube map. So you give it like 6 phases of your die, and then this somehow this becomes the radius at each point along the shape. The other way to do it, of course, is there's a good physics program. There's a spherical harmonics expansion. So you just give it a list of your spherical harmonics and then the intensity, and this then becomes yeah, different shapes. So, yeah, so I've talked a little bit now. I think, yeah, the impression I got was like, if you guys are interested in more, I should keep talking, but I'm also not sure if you're just waiting to be finished. This is the broad overview of how Scatman works. But yeah, are there any questions or something? Mm, okay, no. Um, yeah, I'm not sure I have that much more to, and we can keep looking at the patterns if you want, but this is maybe also more interesting to do on your own. So yeah, okay. Yeah, then I don't know if I have that much more to say. I hope this has been kind of helpful, kind of interesting. Um, let's just double check. Yeah, I've been over. One thing you may notice if you're trying to install this on your own is I should probably talk a little bit about this. Obviously, right when I go here and this is ah okay, this is the file I wanted. Um, ah, what? Ah, I don't know how that ended there. Yeah, but so it's not it doesn't take that long to run through this. It takes a bit more to run through like the 20-ish different shapes here, but this is still reasonably quick. But if you're really trying to do like that's the image I was looking for. Um, right, if you really wanna retrieve a shape, then often you need to have a good idea about what kind of volume you are using, and then you need to just test a lot of different permutations of these volumes. And this can be uh, quite long. So I have been uh, so one thing that oh, this is not the right password, sorry. One thing Scatman supports is that you can do it with CUDA instead. And then obviously this becomes much faster. So if you're really, yeah. So for example, I have been what's the name of the no yeah one thing I have been playing a little bit around with is we've been trying to do this uh shape retrieval on some images we had from a beam time and uh do these images we probably will not uh, manage to do. This is just tests. So anyways, but let me show you one of the logs from running this as a hmm, uh, okay, this doesn't have any interesting information. The thing I can tell you is it took like 12 hours to run through 1,000 iterations of the fitting algorithm or something. And this is using this wibbly wobbly. So this is partially my own fault because you have 200 I was trying to do a 6 times 6 times 6 matrix, and then you have 216 dimensions that you need to fit in, and you really cannot fit with like just gradient descent because these images don't like right they change in weird ways when you change them. So you need to do some uh, this I'm using this differential evolution function that Skippy has, but sure there's other maybe Simplex could also do it. Either way, you need to sort of like test out the whole, or you need to test a lot of the phase space of your shape basically. Uh, and this just takes a long time. So even with CUDA, this can be a very, very long process. But yeah, I don't know what was I trying to show you anything here other than this. Oh yeah. Yeah, just just to say that like we have two, obviously this is not the most impressive clusters in the world, but we have two graphics card clusters here, even then you do 216 times 1,000 iterations, and this is quickly runs up into yeah long run times. If you want if you want to have a good overview of how this MSFT works, there's a paper on it by this Alessandro Colombo, and it's called the Scatman. And also there's a paper on a more modern technique, um, which it's similar but a bit more precise. This is called the propagating, so PMSFT, and yeah, they have a little nice diagram of how you should think about it. So MSFT, you really only uh, you use the density of the material to sort of to weight uh, a little bit this scattering. So obviously, if you are deep in your particle and it has a high delta parameter, I think is the one that does the absorption. Uh, then you have less the layer matters less because there's less scattering in that layer. But this PMSFT is really uh, yeah, you can through this a combination of like Fourier transforming and then Fourier transforming back, you can think of this as like you take each slice and then also whatever the slice generates as propagation is also goes into the next layers. Um, but I think my impression is yeah um, it's not as parallel. It's not as easy to run on a graphics card, but um, this is called this is this one if you want to find it. Um, Yeah. So I think Marcel was here for a minute. Now he's gone again. Maybe he's jumping on his own PC instead. Yeah. Any other questions? Has this been helpful at least or interesting?
Is anything in this software is there to describe the optical property of the shape?
Yes. So when you generate the shape, you give it this delta and beta parameters, and this is then
Okay. Basically angle dependence, yeah?
no, I think you cannot do that sort of thing, right? So you're thinking like, what is this called, bireference or something like this? This is not. You could give your shape different delta and beta parameters depending on. I mean, you set the wavelength and you set the, but by default it doesn't do any.
Density also, na? Density and refractive index like this.
Hmm. Yeah, but by default it's assuming like uh, obviously the shape will somehow influence it, but the yeah.
I mean to say that if suppose a nanoparticle, a spherical nanoparticle is there
Hmm.
of different two types of material, both
Hmm.
has different optical property but have
Yes.
identical shape.
Okay. Yeah, this is. I mean, this can be done. So there are these like. I think we mostly looked at these um, red something like this or the shell sphere shape. These are generally one beta and one delta parameter all the way through.
Okay.
Um, there's this, but this one, right? This is pink and blue, so uh, here you can set two different delta and beta parameters, and here you can set two different optical parameters for. Um, and also, like if you go all the way down to here at this volume distribution, if
Okay.
you're willing to just completely make up your own shape, uh, you can make it as complex as you want, basically.
Okay.
Uh, this is one of the nice things is you don't have to match the grid exactly for the simulations because it'll just do like an interpolation between your so you make your volume distribution as detailed as you need it to be to capture the shape, and then it'll itself interpolate into what is uh, the right level of detail for the amount of scattering or for the scattering angle that you have chosen. So
Okay. Okay. Thank you.
yeah, but I think most of these shapes they assume isotropic material, like the shell sphere and the moon sphere. These can do different things, and then of course this one down here.
You mean
Yeah.
homogeneous, right?
Homogeneous. Yeah.
Homogeneous
Yes.
density and homogeneous index of refraction.
Yes. Yeah. I guess isotropic would be a sphere. Just yeah.
Yeah.
Anyways. Yeah. So yeah, um, I'm not sure there's anything I've talked a little bit about the Scatman and shown some of the uh, yeah how you work with it, but I'm not sure
Have you
there's
gone
like
through any examples?
I showed off a couple of these. Actually, okay, I only showed off the boring ones, which are just these guys. Um, we can take one of this. I think this one is more interesting, probably. Uh, this is This is using one of the shapes from this shape library. I talked a little bit. This is not here. Yeah.
So which shape is it?
Good question. This is number 14, right? So this is see. I think it is a dodecahedron. Let's see if I can. I had the other. Oh, here we are. Okay. They don't have dodecahedrons here. Let's go find another one. Yeah. Okay. This one is, I think, an icosahedron, but
it has 6-fold symmetry there.
yeah.
Okay, yeah, but okay, then it depends on the orientation actually, whether it's 6-fold or
Yes.
5-fold. Okay.
Yeah. So what we could do is let's make another one of these. This is 16, I think. Yeah. Have I imported my shape functions? I don't think I do. No. Yeah. So another parameter that most of these they make icosahedron. No. Uh, There's probably something wrong because it's not letting me tab complete this. But anyways, dum. Yes. We need to add a little star because. Okay. Another thing that most of these shapes support is that you can give it like a rotation. So there's like three different rotation parameters. There's rotation, latitude. So this is, you imagine you have a globe and you tilt it like this. And then there's longitude. So you have a globe and yeah, I guess this would be this way. Rotation is the last one, which I guess means it goes like this, probably. So yeah, this is image 2 is the thing that is changing by maybe we can find the place where it shows 5, but
And that could also be
So-
interesting to see for the cube, right? Because like yesterday we looked at the cube where really this image, the diffraction, this pattern changes a lot whether you strike the cube face on or side on or
Yeah.
corner on. I think there even probably also the symmetry changes.
This is also, yeah. Yeah, we can look at this quickly. So I don't have a make cube, so what you can do is instead you just give it like a little rectangle full of ones. Well, it's a cube full of ones, right? So 3 by 3 by 3. This should be more than fine. And then D type. I don't know if this matters, but volume map expects to see booleans. And actually, let me do 10, 10, and 10. And then the other thing you need to give volume map, which is you need to give it the distance between the points. So let's say 200 nanometers between the points. Ah. So this is here's our cube. Let me set it back to 0. Yeah. So this is going straight through the face of a cube.
And what's image 1?
Image 1 is, I think, this is we were talking about looking at a cylinder. This is the cylinder on the wrong side.
Okay.
So we are going through. Yeah, it's basically
a slit, more or less, or something
slit.
similar.
Yeah. I guess yes, the opposite of a. We can just do plot postcard instead. I think that's maybe more. We don't have this other image. So.
Mm-hmm.
Yeah, and then I guess if we wanna take a look, like this would be the cube. So if I'm guessing right, this will only rotate it. I guess we will see. Which it does, but it also. This is more clearly defined than the rotated one.
Mm-hmm.
This is possibly because when we rotate it, some of the edges might end up outside of the, because this is just completely filled. It might have been better to do, a shape full of zeros, and then in the middle you put a little.
Yes, of course.
So there's some empty space around. We can try this. So something like this, I think. Oh, wait, no, I need to add. And then we're just setting the middle to. So ah, looks cleaner. Not as clean as the first one, but yeah.
Why not making this zero space even larger just to be on the safe side?
We can try that. we want the inner 10 to, so if we go from 5 to -5.
Yes, that looks very clean.
Okay, so we looked at the rotation. So now if we try the latitude, we will be tilting the cube forward, I guess. 20 degrees. Let's see.
Huh. Yeah, it makes sense that like in one direction, forward, let's say. Yes. So the streak, the vertical streak comes from the fact that the two like left and right faces are still parallel. So it still gives us the, let's say, the vertical slit effect.
Mhm.
But the upper top and bottom faces now are tilted, so they don't create an interference, or they don't create a slit, the slit effect anymore. I guess that's the way I would understand it.
Guess that makes, yeah. I guess
Like,
if you look at it from a if you project down the shape into 2D, then also when you rotate it like this, you are kind of elongating the shape a little bit.
yes.
This is, yeah.
But like in general, these very elongated streaks, these prominent elongated features always come when you have at least two faces, like two surfaces being parallel to one another along the beam direction. Like whenever you get this like a slit effect of then you get these very strong streak patterns. So like also if you have some kind of ellipsoid, for example, and or a sphere, which is first of all spherical, but then you just flatten, let's say, the North Pole and the South Pole, make this a little bit flat surfaces, so they start to produce two small parallel surfaces. Then immediately this creates an elongated streak in the diffraction pattern. So that's I found that the first time I saw this, I found this like amazing how like this diffraction imaging technique like enhances any periodic, or even if it like the periodicity is just amounts to two features, but whenever you have some parallel, or ideally even like repeated parallel surfaces, then this creates a very strongly enhanced like elongated streak pattern in the diffraction. So these kind of shape changes are strongly enhanced.
Okay.
But yeah, I mean, can we tilt the cube even more, like
Yes, let
45
me go back
degrees, for example?
Yeah, sure.
Yeah, okay, then now we basically get interference really only in one direction. And if we hit the corner.
Mm-hmm. So longitude and latitude 45, this would then be like so. So we should hit a corner.
Okay, yeah, that looks very different. This already gives an impression that when you do this diffraction imaging on some micro or nanocrystalline structures, then if you really want to figure out and be sure what the structure, the actual real space structure is, it takes many different snapshots for many different orientations, right? To really get the full 3D image, or not image, but the 3D actual distribution in real space. So that's why it needs this like serial femtosecond crystallography. Just one projection, one diffraction image is not oftentimes not enough to give a like really allowed for a reliable full 3D reconstruction.
Anyways,
Had you looked at there was this pill-shaped predefined thingy, wasn't it? Like this or dumbbell?
yes, the
Like
dumbbell, yeah.
since we were talking about this effect of, I mean, is it possible to go from like ellipsoidal towards dumbbell? So then eventually there should be the point where there's really like a small cylindrical part where two.
Uh,
I mean, just to see if this effect can be reproduced that whenever you like change the shape gradually from, let's say, round towards then having a two flattened parallel surfaces, how this, or I don't know, maybe you have looked at similar things already. So,
no, we have
no.
not. I think it would be. I have there's a dumbbell shape, but that's a dumbbell with a. This is still. We could look
Yeah.
at the dumbbell with the um making the length longer. But yeah,
Yeah,
I
yeah.
guess
Yeah. What are
uh,
the control parameters there?
yeah. So this has yeah. I think the ends are ellipsoids, right? And then in the middle you have this L, which is the length between the points. And I my impression is set is the thickness at them in the middle, because if you set this to I'll try showing this. Oh, what? So I think it goes let's see, ABC and then no L first and then ABC set. So make this 800, 800, 800. Then we have a round edge, and then this we do 24, and then set this to 800. Then this should be a cylinder. Um, a cylinder with capped edges.
Mm-hmm.
And then I guess we can make it a bit more elliptical by doing, if we set a little bit higher, this should then stop being a cylinder. It should be something else.
Interesting.
Oh, but so the thing I actually, the reason I think set is the height is if you set it to 0, you should right then. Okay. I was gonna say then you have two balls. Just
Yes, I think
this.
that's correct. This looks very similar to this what we saw in this diffraction images of just two circular apertures, like what you find in this animation on Wikipedia, or two circles separated by some distance. I think that it was exactly that.
Yeah, I guess this is. We'll just quickly do that rotation to 90. Because I think the way this is going is it's going through the dumbbell. in this direction. So they should be closer to the Wikipedia handle. Oh. Okay.
Actually, let me see. Yeah, that's exactly that. I mean, just if I may quickly share my screen for just a few seconds, there's this actually this is also in the PowerPoint slides that are the PDF copy of the PowerPoint slides of my last presentation. I didn't show it, but this is just taken from a textbook. The diffraction images for different scattering arrays, and yeah. Anyway,
If you
and
click,
yeah, it's a different screen, right?
I think maybe display settings up at the top. I'll do duplicate. Yeah.
But the wrong one.
Duplicate should work.
Okay.
Try clicking this display settings up at the top of your slideshow.
Display.
This-
Where is that?
all the way at the top above the image.
I cannot see it because there's this zoom bar and okay, now I can see it. But I cannot change it.
Okay. Then
Showed with a, yeah, anyway, it's I think just from Wilmot's book, it shows these patterns for like two circular apertures. That's, I think, exactly what we see on your distribution, right? And then for like the more periodic arrangement of or periodic array of these apertures, then the more pronounced becomes the like the periodic pattern, and the less pronounced becomes the circular pattern from the like the elementary aperture. But I think what we saw in your distribution, wasn't it just this distribution from the pattern from the double aperture? So that makes good sense. And actually, yeah, speaking of dumbbell, that maybe I could quickly share one more example. I mean, we were supposed to have a presentation by a student given about a very interesting coherent diffraction imaging work about, of course, helium nanodroplets. What else can it be? Actually, this was the very first CDI experiment on helium nanodroplets. Where do I have it? Or just to see Where is it, Gomez? That's this one. Science,
Not
this one.
Bruno's paper. The Fermi one, Masa?
Yeah, I was
Fermi
looking for
20.
this one because that's like the seminal one. Do you see my? No, you don't see my screen. I have to share again. This one. Do you see my screen?
Yeah.
Yep. Okay. So these were the very first X-ray coherent diffraction images of helium nanodroplets, and I mean that's what I was mainly referring to when I said that there's this, as soon as the spherical shape, which produces these circular diffraction patterns, which we have talked about already. Of course, when it becomes ellipsoidal, then also the diffraction image starts to be. But as soon as you get like two flat surfaces that become parallel to one another, then yeah, this like slight change of the shape of the ball becoming flattened, then manifests itself as this very elongated streak pattern. So this was the first evidence of helium nanodroplets actually not being perfectly spherical, but coming in different types of these prolate and no, this is oblate shape. But I think they also, so there's distributions of different mostly oblate shapes, but they can also be pill shapes for large helium droplets. And the conclusion was that these large helium droplets in the formation process, as the helium flows out of the nozzle, this is illustrated here, since to produce these large helium droplets, it's actually the liquid helium that is ejected into the vacuum. And this liquid helium then fragments into these large chunks of, or large droplets of helium. But as the liquid helium or superfluid helium flows out of the orifice, it acquires angular momentum. And so these are actually spinning helium droplets. And due to their rotation, the shape is not spherical, but has this elongated or prolate or oblate shapes. And I mean, in addition to that, so the main striking feature then from this very first work, and this has been confirmed in many other subsequent experiments now, is that I mean, helium nanodroplets are superfluid. Yeah, that's one of the striking properties. And a superfluid, maybe some of you remember from condensed matter physics, a superfluid does in principle not sustain any rotation. But if now the system is forced to rotate, or in the classical experiment, you would rotate the bucket of helium before the transition, before it undergoes the transition towards superfluidity, so that there is already a rotation, angular momentum in the fluid at the point when it crosses the lambda point to become superfluid, then there is obviously rotate some angular momentum in the system. Then the angular momentum collapses into these vortices. Yeah, these are, let's say, quantum states of rotation in a superfluid, and can be seen as these like little tornadoes going through the liquid superfluid helium, where really just a few atoms rotate at high speed around each other along this vortex line. This is also called a vortex, and that's where the angular momentum is then concentrated in these helium droplets. And yeah, this can actually be made visible by coherent diffraction imaging. So, I mean, these are just the shapes, but since X-ray allows to have even higher spatial resolution than just imaging the outer shape of the droplet, but we can actually even get information about the inner structure. So that then became visible by producing these periodic and regular like Bragg diffraction type patterns. And I mean, so this looks almost like Bragg peaks in a crystal when you do diffraction imaging of a crystal, but obviously this is it's not a crystal, it's a superfluid helium droplet that contains vortices. But in a way, it is a crystal because these vortices have the properties of repelling each other. Yeah, they interact repulsively, meaning that they try to arrange themselves in a geometry such that the overall energy is minimized, which means they want to all sit at maximum distances to one another. It's like ions trapped in an ion trap, which at low temperature would also form what is called a Coulomb crystal, yeah, because the ions all repel each other, so they would undergo also a transition to some crystal. Here it's the vortices that form this kind of crystalline structure, and that by coherent diffraction imaging then manifests itself as this regular pattern in the diffraction images. And I mean, yeah, this was actually a little bit cheated because it's actually not the helium, the pure helium vortices that were imaged, but because helium has such a small index of refraction that the contrast would be too low to actually visualize these vortex lines. So the trick they did was, as you can see here in the experimental setup or the schematic, these helium nanodroplets were actually passed through what is called a doping cell, like a vapor cell filled with these yellow atoms. So the blue is the helium, the yellow is xenon atoms, and xenon are very heavy rare gas atoms, which have a lot of electrons. So they have a very strong scattering cross-section. And so they use then the property of these vortices to basically suck in any atom that floats around, like a tornado also attracts objects that orbit around the tornado towards the core line. So here the xenon atoms arrange themselves like pearls along a chain of pearls. And since they have such a higher scattering cross-section, then they acted as a contrast agent to actually make these vortex lines visible. So just the helium alone would not have enough contrast to see it. But that was really the striking new finding that you can directly or more or less directly image the formation of these vortices even in these like helium nanodroplets flying through the vacuum. And nowadays the resolution actually has become even much better. So maybe as a last thing about helium nanodroplets, now we can basically zoom into the structure of these vortices and have a look how they look in detail. There is this interesting work. It's called X-ray coherent diffraction imaging by immersion in helium nanodroplets. So it actually the like immersing other species like xenon in this case into the helium nanodroplets has actually a beneficial effect for the imaging because the surrounding helium acts as a like reference system, like in holography a little bit. And yeah, so here, let me see, where do we have nice images? Yeah, so they could then, by doing this iterative phase retrieval, they could really get some idea of how the exact shapes of these vortex lines looked like. And so they are not just straight lines, but more look like these, like, what is it called? Corkscrew shaped, always ending up perpendicular on the surface of the droplet, but then they get these curved shapes because also the surface of the helium droplet is curved. Do we have some more interesting patterns here? No, but I mean, yeah, this is quite impressive that it's possible. So from scattering images like this one, which is where you would think it's a complete mess, and there's hard to extract any useful information. But by doing these clever phase retrieval algorithms, then they and making, and in this case, they used the information, the input information that assuming a spherical helium droplet as, let's say, the framework around these vortex lines, then this helped to reconstruct the structure of these vortex lines inside the droplets. Yeah, in this way. Yeah, so this is imaging superfluidity basically in the live system, more or less. All right, this is all that I wanted to say to this little topic. Unfortunately, we didn't have the students' presentation, but now you have seen the nice pictures. Yeah, I don't know. I mean, it's up to you, Esbjørn, and the rest of the team to look more into some more shapes, or if you have more questions as to how exactly to carry out these kind of simulations. I mean, I think, isn't it that this Scatman package in principle allows to also do this back transformation, or this like iterative fitting of experimental patterns?
Yes, you can do like I think you can do forward fitting, which is it's called in Scatman, which is you make educated guesses on what shape you think you have, and then you just test a lot of shapes.
Yeah.
But Alessandro has another framework for doing this phase retrieval, which is called Spring or something.
Okay.
Sorry. So there is there is something similar, but if you want to do the other method, which is going, this phase retrieval thing.
Yeah. I mean, Alessandro, there is actually a very nice. I mean, okay, maybe if people are interested, there is this one more really cool experiment where they actually were able to image the dynamics of an exploding nanoparticle by this method. What is the name again? That was Simon Dold, I think. Yes. So this is Alessandro, the first author. Okay, now this is also another nice collection of different experimental patterns. That is actually not what I meant, but I mean, this is other examples. Sorry, I meant this one I meant. You see my screen, right?
Yeah.
Yep. So these were okay, these are MD simulations, but these are diffraction experimental images of silver nanoparticles that were where they took snapshots by coherent diffraction imaging. But in addition to that, they had a strong infrared laser pulse coming sometime before, I think a few hundred picoseconds before the imaging pulse. There you can see it here. It's a time delay of 100 up to 2000 picoseconds before the imaging pulse, and also with different intensities. And then they saw that, of course, you get these nanocrystalline structures with these nice regular diffraction patterns. There's also completely round patterns, but then you can also get images from hollow spheres, essentially, or by cranking up the intensity of this first heating pulse, you can actually complete or more or less fragment the particle before taking the snapshot. And that by reconstruction then looks something like that, or for even higher intensity, then eventually the particle completely disintegrates and explodes and fragments into these little fragments. And according to the MD simulations that were accompanying this work, it actually can be simulated that such a silver nanoparticle, when you impulsively heat it by this short and intense infrared pulse, then it starts kind of boiling inside, and then depending on how much you heat it, it actually forms this nano cavity, which can then collapse again and disappear after 400 picoseconds, or it continues first like boiling, growing, and then producing these hollow spheres. Or of course, if the intensity is very high and it gets heated up to 9,000 Kelvin, then the system completely blows up in fragments. So, but I mean, I found this really cool to see. And yeah, okay, you can study this like in phase space or in the thermodynamical phases and phase transitions and things, but that you can actually take snapshots of this melting and nanocavitation phenomenon. This is, I think, quite amazing. Yeah, so that's one of the first pump probe experiments where you then really you can probe the the dynamics of the structural evolution of these nanoparticles. Yeah, I mean, there are similar experiments also with helium nanodroplets, of course. And yeah, Shiva, the one that you mentioned, that was this one here. This is, however, this is not X-ray imaging, but XUV, so much longer wavelength. So the spatial resolution is, of course, not that high, but here they were able to measure, or they saw these like mostly spherical shaped helium droplets, but yeah, some occasions also these prolate and even dumbbell shaped helium droplets. And yeah, since here it was not only small angle scattering, but wide angle scattering, then this produces not only these linear streaks, but if in wide angle scattering for the specific orientations, you get like even bent, like these bent structures. And that's actually better to reconstruct the full three-dimensional distribution than just small angle scattering, because from small angle scattering, essentially you get only the projection, the 2D projection, whereas these images actually contain 3D information at wide angle scattering. But this works for these XUV and helium nanodroplets particularly well, because they used the fact that the wavelength was actually tuned onto a resonance of helium. Helium happens to have these very high-lying excited states at like 20 eV, much higher than any other species. And 20 eV, this is already extreme ultraviolet. So there you can do like diffraction imaging and like kind of spectroscopic resonant excitation at the same time. And this resonant enhancement of the scattering cross-section helps immensely to get these bright images in the case of helium. But that's really a very special case for these high-lying resonances in helium. And I think they had some, there's also this other paper where they did also some dynamics. Where is it? I think this is also long dynamics. droplets. Yes. Yeah, so this is also with short delay. Here 20 or 19 EV. This is again using the helium resonance, but then like without pre-pulse, so just the snapshot of the normal non-excited droplet produces these different shapes that we have seen. Okay, at small delay, 3 picoseconds, then you can already guess that there's some small structural changes appearing compared to the unperturbed droplet. But then for very long, so they could actually do some kind of pump probe curve. I mean, with very coarse sampling, but going up to more than 100 picoseconds, then things really start to change. Then you get some dynamical effects that are very like nicely visible, and in particular, the diffraction images then look very much fragmented and irregular. Here you get these interesting explosion type patterns, which then they try to categorize just more or less into different types of patterns to get some first sorting. So figuring out from these very like highly structured and irregular patterns, trying to understand what exactly is happening and how the actual distributions look like, this becomes very challenging. But so here I think some kind of very like simple forward simulations showed that likely what happens is that actually the droplet does not fully like atomize and explode, but rather these bubbles, like you start boiling the helium inside the droplets, and these small bubbles form, or larger bubbles, and that then manifests itself as these more structured irregular patterns. But this was done by forward fitting, or by, let's say, intelligent guessing, coming up with some guessed distributions, and then calculating the diffraction image, looking which image compares visually more or less. So by far from a reliable, full-fledged phase retrieval and exact structure determination. This is more intelligent guessing. Also, there can be these surface dimples, which produce these interesting spider-like patterns. And speaking of surface dimples in helium nanodroplets, there's another excellent data set that is waiting for being finalized and published, where in a joint experiment with Shiva Ramakrishnan, we did an experiment and imaged some surface explosion and surface dimple formation, which also like produced some kind of patterns similar to those here. Many different interesting things. All right. I didn't want to give another full-fledged presentation. This is just to give you some more glimpse of what's going on in this diffraction imaging community, and like what kind of exciting and interesting nanoparticles and nano droplets you can image. And pump probe dynamics is definitely the way to go in the future to study the dynamic, not only static structures, but actually see how these structures evolve, mostly upon laser irradiation triggering some specific heating or some specific excitation in the droplet or in the nanoparticle. Shiva, is there anything you would like to add?
Yeah, yes, Masal. I think you probably showed this PRL or from the Fermi imaging, which showed this intermediate shapes, pillbox and ellipsoid that you were discussing. Although not atomic resolution, but I think that showed very distinct scattering patterns that were distinct to these shapes. Right. I
Yeah, yeah.
joined a bit late, so I'm just
Hmm.
wondering if you already showed that. That
Yes,
is
just
quite
before we
understood.
just had
Oh,
a
okay.
quick look at that.
So,
Yeah.
oh,
So, I
that's
mean,
wonderful. Oh, I just wanted to ask you, just in, oh yeah, this one, this is the iconic image. So,
yeah.
yes, Marcel, just that I have in mind. I think you did it wonderful. So, I think, yeah, we are coming to the finale to the course. Looks like. So then,
Yeah, I think so. I mean, unless anybody has some more specific wishes, what Asbjørn should magically uh, image and or do in his simulations. Otherwise, again, I think if you like to have or you run into any issues running this Scatman, or you would like, or you haven't gotten around installing Scatman now, but you a little bit later think it might be a good idea to do it, then please contact us, and of course we would be happy to help getting yeah up and running with these simulations. Sorry, Shiva, you wanted to say something more?
oh, perfect, perfect. Yes, Marcel, that's true. And maybe I just maybe would propose if since this looks like a nice bunch of students who will still be at some university or another for some more time, 1, 2, 3, 4 semesters or more. If you come across or you read some nice papers related to this course, we could also have beyond the course some journal clubs. We could organize presentations. This will not be like periodic or part of the course. If there is somebody prepared with this, let's say next month, we could just call on and we'll be happy to listen to your journal club talk. We could maybe extend the journal club as several research students and even otherwise aspiring researchers are in this group, I'm sure. So I would welcome you. Please drop us a note. I'd be happy to take this up with you. So I'll be happy to organize this. Again, we can even record that and keep for our own future references and so on. So cool. But most of all, I'd like to thank Marcel for this remarkable effort. I also say that wholeheartedly, besides Marcel being our collaborator, because we've been working in this field for a while and it's now taken considerable time from Marcel's end in organizing this entire material in a very pedagogic style. So far, we were looking at it sort of paper by paper or like a journal club. So now we have a wonderful platform. And for those of us, including me, who missed some lectures in between, the recordings are there. So we can go through this course gradually and educate ourselves. And in the process, again, recall the exhaustive efforts, the insights,